of the physical universe, following in the example of Galileo, and um, and really we're taking his philosophy. This is kind of a cute statement from Galileo. He was kind of an interesting guy. I've read a couple biographies of him in the past year. The sun, with all those planets revolving around it and dependent upon it, and we'll actually talk about that today, can still ripen a bunch of grapes as if it had nothing else in the universe to do. And that is certainly true. The other thing I want to point out to you is that, let me start recording this. Just a second. Get a mic up. I need a new microphone. I'd like to point out to you that the SI schedule here is now correct. This is Tuesday. Did you guys actually have a session on Tuesday? Did anybody come? Okay, so you guys figured it out. Anyways, for the rest of you, there it is, this time for sure. And hopefully no big disasters from that classroom building 1, room 212 on Tuesdays at 5. Tonight you have a special online session. And, you know, when I made this keynote file this morning, I didn't know, I just said TBA in discussions, but it's actually in discussions, and I'll show you that. Actually, let me show it to you right now. Hold on a second. Let's see if I can get this. Let me show it to you. Okay, if you go back to discussions and look in the pinned discussion about supplemental instruction schedule, you'll see the link. It's right here in blue, and the password is OPAL, all caps, OPAL, and it works really good. It's the Adobe Connect software, and Shai is going to be operating that tonight at 6 o'clock. So be there or be square. Now let me get back over here, and let's talk about this. This slide. You've got grades, and right now the grade book looks kind of like this. Let me blow that up for you a little bit. Here it is. At the very top is a little blurb here that says something about the due dates. The first few items in the grades page, these due dates over here in black in the middle column are false. The reason I set those to be false due dates is because I want those things to float to the top of the display, to the top of the page. So they all have, you know, this is January 12th, 1 a.m. Okay, that was the first day of lecture, just after midnight, and so we didn't really have class then. So hopefully that'll make sense to you that, whoa, Dr. Beast, not even trying to be accurate. This must be false. The accurate stuff is over here on the left in the title. All right, and so early iClicker bonus from January 14th. Yeah, that's when we did that activity, registration and so forth. Exam 1, Thursday, February 4th, next Thursday, a week from today. Yeah, that is accurate. Okay, now it's my way of controlling, trying to get some kind of purchase, a little bit of leverage on Canvas. We used to have the web courses system used to be based on Blackboard, which is a different computer system entirely. Canvas doesn't let me have nearly as much control, and it doesn't let me do nearly the amount of cool things I used to do in Blackboard. But it's what we got, so we got to try to manipulate it and control it as much as we can. All right, now down towards the bottom is where your clicking data is, and that's the really new stuff I want to go over with you. Over here on the left it says L5 answers and L5 correct. Now that's the data that I keep track of using iClicker software and the gradebook software built into iClicker for class participation. And every day I'll be looking at A, how many you answer, and B, how many of those you get correct. So these two numbers, now this is for my demo student account, so this demo student has perfect 5 and 5 here. But you might have a 5 and a 3, or a 4 and a 4, or any kind of combination, and it'll vary on day by day. Some days I'll ask 7 questions. Some days I'll only ask 1 question. But it'll always be up. And then you can look over here at the data that you score, and you can kind of keep track of where you are. And right now we just have 1 lecture. But you can see I'm set up for today's lecture. So we'll be doing some clicking. Have your clicker ready. And when we do that, I'll post the data probably this weekend. And just as a word of warning or caution, sometimes I get a week behind on clicking data, especially like on exam week. Sometimes I'll be rushing like a maniac from another planet to get the exam ready, and I don't always update all the clicking data until after the test is in. So just so you know, I try to do it after every lecture, but I don't always. Sometimes I get a little bit behind. But I always get caught up and stuff like that. All right. Questions about this? Yeah. Brittany.
The only thing that counts for grade-wise is how many we answer, right? Not how many we correct.
Brittany asked me the only thing that counts grade-wise is how many we answer, and she asked me, is that true? And that is not true. The reason is the regular part of your grade that everybody can get, the class participation grade, is based on L5 answers, L6 answers, L7 answers, and on down. You, by the end of the semester, will have maybe over 100, and you want to get 85% of those answered. And if you do, then you get 25. If you get less than 85%, you get some other fraction of 25 points. L5 correct, L6 correct. You want to keep adding those up because that I give you bonus points for. If you get 75% of the questions correct, I give you 4 bonus points. All right, and in a 250-point scale, that's a little over 1%. All right, so that's nifty. And you're going to love having those 4 bonus points. And 75%, if it were a letter grade, that would be a B. So if you get a B on your performance correct on all the clicker questions, you'll get 4 bonus points. So that's my way of rewarding you and giving you motivation to not just, click with your eyes closed, but think about what you do and try to actually get it correct. Okay? Does that answer your question? Good. Another question. I just saw a student back over here go like this. As soon as I asked, is there another question, she went like this. And I thought, oh man, she's faking me out. But yeah, it was you. You did it. Just like this. Anyways, let's keep going. Here's the SI online session again. And we just put this slide in at the beginning of class. So try to do that tonight. See how you like it. And also, Shai, the online section will be allowed to attend that as well. So they're working from the same lecture, so it should be coherent for all you guys. And for those of you that want to try it, if you have an iPhone with the white earbuds that have the microphone over here, you can use that. Just plug it into your Mac and use that. If you have a fancier set of headphones with a microphone, so much the better. The built-in microphone really sucks because it's so close to the speakers that you get a lot of feedback and echo and stuff like that. But something like this, it's really sweet. Question? What's that? The question was, are they going to be recorded? And the answer to that is yes. Did they show you how to? Okay, I always record mine. I do my office hours in the online physical science with the same software, and I always record it. And Shai's going to record it. So if you miss it, you can still go and look at the recording. And Shai, can you post the link for the recording inside discussions as well? All right, that'll be great. And so yeah, that's, because, sometimes you're busy or sometimes you forget. But hopefully if you can get in there and listen to it, it'll be helpful, even if you can't participate. Okay, let's get back to Newton's laws of motion. I love this picture. This is actually a postage stamp from Germany, Deutsche Bundespost, concerning Sir Isaac Newton. And you can see a little equation up here, delta mv in parentheses equals F times delta T. We're going to be talking about that probably on Monday. That's known as impulse, the impulse equation. And behind that, there's a rainbow, and there's a diagram of a prism. So it's kind of a cool deal. Now, what I want to do is go back to the second law with you, and then onward to the third law. And as I mentioned on Tuesday, the first law, the law of inertia, it's basically a way of asking what states of motion are consistent with the absence of forces or with the existence of forces that balance. Because if you have balancing forces, you have a net force of 0. If you don't have any forces, you're way out in between the galaxies and there's no gravitational force acting on you hardly, then that's actually no forces. What's the state of motion consistent with that? Or if you're on that mythical frictionless ice skating rink where the upward rigidity force of the ice holds you up against the downward weight force from pull of Earth, that's not an absence of force, but it is balanced forces, a balanced pair of forces. What states of motion are consistent with that? And the states of motion that are consistent with that, according to Aristotle, is rest. But according to Galileo said, yeah, rest is good, no forces, good, but also constant velocity, a state of constant velocity, or an inertial motion, they call it sometimes. Constant speed and constant direction, constant velocity. And second law is, all right, how does your state of motion change if you don't have balanced forces? And that's what we want to talk about here. Now, last time we talked about F equals ma. And these are the two different ways, two of the three different ways. It's a pretty simple formula. I guess you could have m equals F net over A. But usually these are the two that we work with. Now that F net over there, that can be any kind of a push or any kind of a pull. So if you erase it, you could put in some kind of gravitational force. Okay, the force of Earth pulling down on you. The force of Earth gravitationally pulling down on an apple tree, and so forth. Or you could have an electromagnetic interaction force there, or even a nuclear force, one of the two kinds of nuclear forces. This is actually the conceptual version of it, in other words, figuring out an acceleration, it's good to know a push or a pull. That's the numerator. And it's good to know how big of an object you're trying to push or pull. That's in the denominator, the mass, the measure of the inertia. Another thing that we did last time was we actually worked out the weight force, W. Go ahead and write that down. I didn't write it down on the slide here. Capital W for weight force equals mg. It's just a specialized version of F equals ma. Weight force, capital W, equals mass of the object times the acceleration due to gravity, 9.8 meters per second squared. And if you need to, use a minus sign if you're trying to figure out up and down forces. And we did that for a T-Rex. Now, most of you got this answer correct. I want to give you just a little tip on how, if you're in the middle of a test, how do you know that the number you're clicking in is at least in the right ballpark? Well, with a weight force, it's fairly easy. Because what you do with a weight force to estimate it is to take the mass, 342 kilograms, and just add a 0. Multiply it by 10. Because gravity itself, G, is 9.8, and that's pretty close to 10. So if you're estimating, 3420 is easy to just write that down. You read the problem, you write down, okay, I better come in at about 3420. And then when you go to your calculator, or even better, if you're on pencil and paper and you don't have a calculator, and you're a little bit rusty on your multiplication without a calculator, and you want to think, okay, does this look right? Then, you say, all right, I better get something close to 3420. And then you calculate it out, and that's fairly close. 3420 rounds off to 3400. And 3352 rounds up to 3400. So these are fairly close. And if you have a calculator, you buzz right to it. But if you're trying to make sure, you did your calculator and you're nervous, and on exam 1, there's going to be a lot of nervous people in here. I mean, much as I love working with students, and much as I enjoy working with students, I know that especially on exam 1, there's going to be a lot of nervousness. It's normal, okay? But this, hopefully, if you can remember this, wherever you find it, a task that requires this on exam 1, you can be a little bit less nervous. And that's good because that means you work faster and you don't get all nervous up and start blanking out the information you need. Just cruise right on through. All right, and that's what we want. All right, so that was last time. That was one of our easy calculations, the T-Rex. Let's do a little bit more discussion. All right, so we're still on the second law. And here's the second law over here. In the acceleration format, acceleration A equals net force divided by the mass, m. And over here, here's the definition of acceleration. Delta V over delta T. The time rate of change of the velocity, or the time rate of change of the speed. If you're working in one direction only and you're only decelerating or only accelerating, then just, you don't have any need to worry about minus signs for direction. But if you're working left and right, yeah, then you want to pay attention to directions. But anyways, and here's the other version of Newton's second law. Now, if you put this version here of A into this equation, F equals ma, then it's going to look a little bit like this. Well, it's going to look exactly like that. I shouldn't say a little bit. It's going to look exactly like that. F equals m times the quotient delta V over delta T. And hey, that quotient, that's just acceleration. So we're looking all right. But the reason I like this is because, and I'll put a red box around it, it really helps you interpret forces and motions. So for instance, delta T in the numerator is the elapsed time during which you're accelerating. Delta T in the denominator is the elapsed time during which you're experiencing the force. Delta T in the denominator is the elapsed time during which V is changing, and you're getting a delta V other than 0. All right, so there's a lot of ways to interpret delta V. Delta T. Delta V, that's up in the numerator. And mass is here. That's in the numerator. I mean, you could put it up on top, make a big fraction bar and put m delta V in the top of the big fraction bar. But one thing I want to ask you, last time I mentioned that old corny joke for when you were in third grade, you try to trip up your buddies after school, you're at the playground or whatnot, and you say, okay, genius, which is heavier, a ton of feathers or a ton of bricks? And if the guy's, thinking, yeah, I'm pretty smart, it's got to be a ton of bricks, he's wrong because they're both the same weight. Okay, similarly, you might ask yourself, if you're going 60 miles an hour, and this is not really a joke, but it's a serious question, and a serious comparison, if you're going 60 miles an hour let me make it a little bit safer. If you're going 10 miles an hour in a car, which object would you rather have bring you to a stop? A telephone pole or a snowdrift? Snowdrift or telephone pole? Which one would you rather have bring you to a stop from 10? Raise your hand if you have an idea on which you'd prefer. Snowdrift or do you have a suggestion? Okay, here's one answer. It doesn't really matter because if they stop you and you're starting from the same speed, 10 miles per hour each time, it doesn't really matter. Who has a different, and that's definitely a kosher way to look at it. Who has a different opinion? Which one would your car rather have to stop them? A telephone pole or a snowdrift? No, that's not a physics term. That's a lunchroom term. That's over in the student union, What is it about the snowdrift? And there's another opinion. The snowdrift is the one that the car would like. But why is that? In terms of this equation here, what does a snowdrift do to this equation versus what a telephone pole does to this equation? You want to think. Snowdrift. M delta V over delta T. Telephone pole. Raise your hand if you have an idea. What do you think the snowdrift versus the telephone pole? I see your hand, Alana. I want to see if somebody else can. What do you think?
I think that snowdrift, the force would evenly distribute, so the car would be at an advantage, versus the pole, the force would be at one point.
Okay, that's a valid point. Okay, so the force is going to be distributed over the front of the car instead of just like this much of the car. Okay, good. But what if instead of a telephone pole, it was a brick wall? So let me modify my question now. What's the advantage to a snowdrift, if there is one, in terms of this equation compared to a telephone pole or a brick wall? And I see your hand. Did you have an opinion over there?
Time to
For which? The snow pile or the snowdrift? Okay, the snow. So, what's your first name again? Carl. Carl says that the snowdrift, and for those of you from Florida, snowdrift is like this big pile of white crystalline water that happens when it gets really cold. You probably have no direct experience of it, but many of us that have lived up north, if you do plow into car, it increases delta T. All right, so make a note. Snowdrift increases delta T. Brick wall or telephone pole decreases delta T. Now, if you have a big number in the denominator, your fraction there is going to be tiny. All right, so the snowdrift, tiny fraction from delta T. Because your delta V is negative 10 miles an hour. I mean, you're going from 10 miles an hour this way to 0, so that's minus 10 miles an hour. Right? So the numerators are the same, and if it's the same car, 1,000 kilograms or whatever it happens to be, that's going to be the same. So the only thing that's going to change between a snowdrift and a telephone pole or a brick wall is delta T. And with a brick wall, delta T is tiny, really tiny. I mean, you're going to stop, bang, right like that. And so it's a big fraction. So telephone pole / brick wall, small delta T, big quotient, big fraction. And therefore, big stopping force. And that is why when you get stopped by a telephone pole or a brick wall, it'll wreck your vehicle. So your vehicle may not like it too much. But a snowdrift, boy, you can do that every day. All right? Unless you stop by the snowdrift and then go over a cliff, and then, but that's like in a Bugs Bunny cartoon. So here's another example of that. Say you're at the gym and it's plyometrics day for you. You're getting ready for a marathon or what do they call that stuff? UFC? What does that mean, UFC, anyways? Unrestricted? Ultimate Fighting. So, Ultimate Fighting, I don't really watch that stuff, but I see it mentioned on TV and stuff. UFC. So you're getting ready for that. You're working with Chuck Norris. You're doing some plyometrics, and so one of the plyometric things is box jumping. Okay, so what you want in something like that is you want to bend your knees, at least a little bit, and when you do that, that's going to be easier on your knees. If you bend your knees, that means most of the mass of your body comes to a stop in the vertical motion over a longer delta T. Now your feet come to a stop immediately, but the rest of your body kind of eases down in a big fraction of a second or so. And that's a little easier on your knees because the stopping time is longer, and therefore the stopping force is smaller. All right? And there's a jillion different ways to look at that stopping force. But it all goes back to this particular formula right here. M times delta V over delta T. So there's a lot in that formula that you can use to interpret the motion and the forces that produce the changes in the motion of anything that you're trying to look at, whether it's plyometrics or putting a spacecraft in orbit around the moon. You got to figure out all that stuff. Now, I want to do some practice with you on iClicker, so get just like these little hound dogs, 4 hound dog buddies. Let's do a little second law practice. So get your clicker ready. And we'll have some questions today in iClicker. And again, we're on frequency BB, so if this is the first day that you've used your iClicker, hold the power button down until you get the flashing square, and then type BB. Also, I want to mention something to you. A student texted me, said, Dr. B, I thought I answered all the questions and got them all right. And I have a feeling that some of the calculation questions yesterday didn't get sent. And there's a difference that I may not have emphasized yesterday, but let me do it today. On multiple choice questions, like the one we're about to do, the clicker, if it knows that you're on a multiple choice question, and therefore as soon as you hit one of the A, B, C, D, or E buttons, it sends it. When you hit the refresh button and start a numeric answer like we did yesterday, remember when on Tuesday, remember when I said hit the refresh button a couple times? That allows your clicker to know, it refreshes itself, and it basically asks my computer, okay, what's cooking? What do you got coming at me? And my computer will say, numeric question. And so the iClicker goes into numeric question mode, and in numeric question mode, you have to hit the send key. All right? And so I think for those of you that are thinking, dude, I answered all 5 questions and I got all of them right, why do I have 2 and 1 for my iClicker data? L5 answered, L5 correct. It's possibly because of that. You didn't hit the send key. All right, so try to remember that, and I'll try to reinforce it with you as we go. Here's a question. Metric unit of force. This stamp makes Newton look like he was in a heavy metal band or something like that. Hairstyles, I tell you. He was active in the 1600s, late 1600s. See there, 1643 to 1727. Very interesting, another very interesting guy. But Galileo was his master. He was a student of Galileo. 20 seconds. 10, 9, 8, 7. Answer your question. 6, 5, 4, 3, 2, 1, 0. Get it in, because I'm going to stop it. Once I hit the stop key here, then I stop listening. All right, so let's see. Stop. Yeah, most of you got it. Combination of mass, distance, and time measurements. And remember last time I mentioned to you that the metric unit of force, the Newton, is a kilogram meter per second squared. And students, make a note to yourself. The Newton is a derived unit. It is not a fundamental unit. Meter is fundamental. Second is fundamental. Certain fraction of a day. Mass is kilogram is fundamental. Certain amount of liters of water or certain number of grams of water. And that's based on the meter. But Newton's velocity is derived, meters per second. It's derived from measurements. Acceleration is derived. We don't really have a metric unit for velocity. I mean, we talk about meters per second, but that's not the metric unit for velocity. But Newton's is. Now, I want to talk a little bit more about directionality. in Newton's second law. Now, up here in the upper right is the second law, and notice that I've got a couple little teeny arrows above the letter F, capital F, to signify that the force is a vector. It can be represented graphically with an arrow of a certain length. Also, the symbol A, lowercase a, also has a little teeny arrow, and that symbolizes that the acceleration is a directed quantity, a vector, and that the acceleration can also be represented by a different flavor of arrows, a different flavor of arrow. You cannot mix those two arrows. That's like mixing apples and oranges. You don't want to do that. You can draw them on the same diagram, but you should try to make them look different, a little bit different anyways, or at least label them as an acceleration and a force. But if you are making a diagram, the acceleration and the force are in the same direction. And that is because the mass is a scalar quantity. And it has no direction. So there's no change, no twist that comes from the mass dependence here. Inertia is directionless. It's kind of interesting that it is. So if you measure the acceleration, that tells you the direction of the net force. Let me repeat that. Measure the acceleration, and you will know the direction of the net force. Here's an opposite view of that. The acceleration does not necessarily tell you the direction of the constituent forces. So constituent forces means all the different forces that you add together to get a net force. Net force is the sum, the vector sum of all of them. So a constituent force on the mythical ice skating rink is the rigidity force upward. And another constituent force on the ice skater is the weight force downward. Okay, so, but those two constituent forces add up to a net force of 0. Unless you're not on the mythical frictionless ice skating rink. If you're on a real ice skating rink in a pond and the ice is too thick, the ice is too thin, the ice will no longer be able to support your weight, and down you go into the cold, cold water, which is really dangerous. So you don't want to skate on thin ice, which we don't really have to worry about that here in Florida. But so let's take a look at an example here. If you get a force like you're driving around in a Ferrari here, okay, and so here's forward direction, here's aft, and starboard is off here to the right, port is to the left, for the driver anyways. And let's say that you get a force 45 degrees from your velocity. So you're moving forward and you get a little bump from something in that direction. And you will get a speed change from the forward newtons that this thing delivers to your car. So that's like, somebody bumping it. I don't want to, I hope nobody has to go through it, but I mean, if you get in a car accident, the car accident, if it comes at an angle, it'll bump you forward and it'll bump you to the right. This one would anyways, if it's coming in from port. The direction change comes from the starboard newtons. So this impactor here, this little kind of yellowish bowling ball, if you will, is going to give you some forward newtons of force and some starboard newtons of force. And when it does, the forward newtons will change the speed. So you'll go from 30 miles an hour to 31 or something like that. And then the newtons that come in from the side to starboard they're going to change the direction. So, and you're not even going to notice it. You're going to be going off in a different direction at 31 miles an hour. All right. So the direction of the forces comes from the direction of the acceleration, the change in the velocity comes from the net force. Okay, third law. Let's talk about this for a few minutes. Action and reaction. And this is kind of a cool law. And this particular running back, I can't remember who this is. Is this Standback? Or I can't remember who number 35 is. I should know the answer to that. Anyways, when you push off, your opposite pushes you back. For instance, with two skateboards. Hey, do we have any? Raise your hand if you have got your skateboard today. Skateboard. One. Anybody else have a skateboard today? I see one in the back there. Is that yours? Way back there? Whose is that back there? So that's nobody's skateboard back there? It's somebody's skateboard it's a wuss. It's chickening out. You don't have your skateboard today? Caitlin, no skateboard today? Huh? Dude. So we only have one skateboarder with guts? All right. Come on up. And bring thy skateboard. And let me I keep fooling around with my earphones here. I shouldn't do that. All right. He's going back to get his skateboard. What's your name? SATA? Sava. Oh, stop. Stop where you are. Get on your skateboard and roll down come on, this is physics class. If you got there we go. Acceleration. All right, now, Sava, I want you to come up here and face the wall. Bring your skateboard and right over here. Okay, and I want you to face the wall and get right up to the wall. Okay. I want you on the skateboard. Okay. Now Sava is going to push on the wall, and he's a big, strong guy. He's going to push this way into the wall. Now the wall is going to, it ain't moving. It's not going to, he's a big, strong guy, but he's no Arnold. He's not a Terminator. Okay? So he's going to push on the wall, and what happens?
You want me to do it?
Go ahead. Whoa. His state of motion changed. He pushed that way, but for some reason, his state of motion, his delta V, was this way. Therefore, there's a net force on Sava this way. And where did that come from? The rigidity force of the wall. So all those little shrimpy molecules, zillions of them, were pushing around Mr. Sava up here. All right, so we had a delta V. So here's your notes. Sava's delta V is in let's call this the Z-axis, okay, toward you guys. From the front towards the back of the room is Z-axis. So he had a positive, delta V was positive in the Z direction. Okay, so here's X, left and right. Here's Y, up and down. And then the third dimension, Z, is toward or away, and toward is positive. Toward you guys is positive. So Sava had some delta V in the positive Z direction. All right? That means he had a net force in the positive Z direction. Even though he pushed. So make a note of this. Sava pushed in the negative Z direction. And his push back was in the positive that he got from the wall was in the positive Z direction. Thanks, Sava. Great work today. And let's give Saba a hand. And in doing that, and I'm going to keep an eye on who picks up that skateboard in the back there. I'm going to know who's a weenie in this class. Anyways, thanks, Saba. That helps out. So the third law, this is what Sir Isaac Newton figured out. The third law, that if you push something, that something is going to push you back. All right? Those two forces form a pair, and we call them a third law pair. So every time there's an interaction, there's a pair of forces. One on one object and the other on the other object. And here's another way to write it. Whenever two objects interact, the force exerted on one object is equal in size and opposite in direction to the force exerted on the other object. Okay, and Sava and the wall are good examples of that. Now, the wall didn't really take any delta V because it's rigid. Okay? And actually maybe it flexed inward in the negative Z direction, by like a millionth of a meter or something like that. It probably didn't flex that much at all. And here's another quote from page 41. An object that exerts a force on another object also experiences an equal force from that other object, but in the opposite direction. And hey, you guys, we're in chapter 3 of the ebook now. All right? And I'm working on a free chapter for you that you're going to be able to download in PDF maybe in about a week or so to follow up on this information on forces. All right, so that's the third law. Now let's focus in so just make a note, page 41. An object that exerts a force, etc., etc. Let's focus in on this football player. Now, if you've ever been on a track team and you run a sprint event, a lot of times the track coach, the sprints coach, will tell you to think about your running motion as if your feet were throwing the track behind you. So if you have a football, you're throwing it like this. If you have a baseball, you're throwing it like this, right? That's what you do with a baseball. But track guys, some coaches teach to throw the track behind you. And so this particular football player, he's throwing his foot, and you can see he's up here on his tippy toes, right there. That's the only contact he has. All right? So all of his forces are acting at that particular location. All right? So here's his force. It's downward and behind him, roughly, in this diagram. All right? Now, equal but opposite force that he experiences from the ground is this way. Upward and to the front. So the ground actually pushes him. And what direction? It pushes him upward. Okay, which is good because it has to support him against gravity. And it pushes him forward. He's pushing back. He's throwing the field behind him. The field's pushing him further up the field. All right, toward the goal line. And away he goes. All right. Now, a little kind of extreme counterexample to this, conventional field, whether it's regular turf or if it's artificial turf, they're pretty solid. But, you can't play football on a field made of Jell-O. And that's like Newton's fourth law, but he decided not to put it in his book. Okay, and the reason for that, you've got to get some pushback force, and so the field needs a little bit of rigidity, and Jell-O just will not. It's good to eat. I mean, it's delicious, but it's not good for playing football. Unless you're so small, like a flea or a mosquito. But for a normal size football player, no, you can't do that. And so that rigidity force is the same force. Remember, as I said before, it's like little teeny tiny trampolines, uniting the substance underfoot or the top of the table, making it rigid so that it might flex a little bit, but it'll always give some pushback. And the pushback, that's actually what pushes him down the field. It's kind of interesting. So he's pretty tired at the end of the day, but his exertions, they were all in the opposite direction. I mean, he's running one way, but he's pushing the other way. But that's how it works. So if you're on a sports team, or if you here's another thing. If you have a friend that's an engineering major, just explain why you have to push backwards in order to go forwards. Or if you want to burn your coach, ask him, well, why do I have to exert backwards force in order to go forward? And he'll say, go ask Dr. B. And this is the explanation for it. Okay, page 45, there's an example of two skateboarders interacting. Go ahead and make a note. A skateboarder example, Carl and Bob. Page 45. Here's the specs for Carl. Now, this is why I wanted to have with you, whoa. Whoa, my connection here is flaking out on me here. Come on, baby. See how it works, Kevin? Darian and Caroline, they're sitting on either side of you. You're not helping me. You're just la-di-da over there. I can't get this thing to reacquire. Let's see if I can do this. Dude, let me try this. Okay. Man, we're in bad shape. Okay, students. Let me check something here. Pretty close to the end of the hour. I wanted to do some more clicking. All right, I'm going to dismiss you. We'll have some homework. It'll be a fairly simple one for the weekend. And students, listen carefully. Before you head out, make sure you study Carl and Bob, page 45, over the weekend. All right, now you're dismissed. I'll see you on Tuesday. Let's get some lights. I do not know what the problem is with this. It is blank. I moved my